Okay. Three liquids of equal masses are taken in three identical cubical vessels A, B, and C. The densities are rho A, rho B, and rho C respectively. But rho A is less than rho B is less than rho C. The force of the cubical vessel is. So the force of the cubical vessel is maximum in vessel A, same in all the three vessels, minimum in vessel C, or maximum in vessel C. So we have the force which is equals to mass into into G, that is into gravity. So as we have M in mass of A, mass of B equals to mass of C, so therefore the force on A equals to the force on B equals to the force on C. Though they have different densities, the forces will be same. So option is B, same in all the vessels. What is the barometric height of a liquid of density 3.2 grams per centimeter cube at the place where that for mercury barometer is 76 centimeters? Okay, so we need to compare the densities of a liquid and that for a mercury barometer. Okay, so we have h1 rho 1 g, which is equals to h2 rho 2 g. These are for the heights, height rho and g for the mercury and for the liquid. Okay, so we need to find the height for the where for the mercury barometer is 76. What is the barometric height of a liquid? So height for a certain liquid we need to find. Let that height be h2. So the equation in terms of h2 will be h1 rho 1 g1 g upon rho 2 g. Okay, so this g gets cancelled, so we are left with h1 rho 1 upon rho 2. So the height of the first liquid is 76 upon its density is 13.6. Okay, upon the second liquid the density is given as 3.2, so that gives you the answer 323 centimeters, that is h2. So C is the correct option. A small cylinder of 2 centimeter diameter is connected to a large cylinder of 20 centimeter diameter, and is incompressible fluid is filled in the cylinder. If the force of 60 Newton is applied to the piston of a small cylinder, then the force exerted on the piston of large cylinder will be. Okay, so here we have two cylinders, one of 2 centimeter diameter and one of 20 centimeter diameters, um, which are connected, and the fluid is filled into it. So we have Pascal's law. According to the Pascal's law, the pressure of the fluid is transmitted in equal directions. So pressure in first fluid is equal to the pressure in the second. Pressure is force upon area, so that is F upon A for both of them. So F of force on one will upon area of one will be force of two upon area of the two. So we need to find the force exerted on the second cylinder. So we can have F2. The equation in terms of F2 becomes F1 upon A 1 into A2. So we have the force on F1 is 60 Newton upon its area is pi r square. So for a cylinder we will be having the area, it is 2 square, so A is pi upon for a cylinder we are having 3 by 4 pi r square, so that will give you 2 by 4 cube square multiplied by pi. For the second area we have 20 by 4 square. Okay, so the answer comes out to be 6000 newtons is the force on the second cylinder. So option B is the correct option. The pressure on a swimmer 10 meters below the surface of the lake is we have to find atmospheric pressure is given. So the total pressure, if the swimmer is swimming, the pressure below the surface of the lake, so total pressure will be the atmospheric pressure plus rho gh, that is equals to the rho will be the density of the water. So the pressure, atmospheric pressure is given as 1.01 into 10 to the power 5 plus rho, the density is 10 to the power 3 multiplied by g, which is 10 multiplied by the height, it is 10 meters. So the total pressure on the swimmer will be, here it becomes 2.10 into 10 to the power 5 pascals, so that is 2 atmospheric pressure. C. The area of cross section of the wider tube is shown in the figure below is 1200 centimeter square. If the mass of 18 kg is placed on the massless piston, what is the difference in the level in the tubes? Okay, so we are given the area 1220 centimeter square. So if a pressure of if a mass of 18 kg is placed on this massless piston, what is the difference in the level of the tube? Okay, the rise in the liquid on the other side we have to find out. So we have force which is equals to m into g, so that is equals to mass is 18 into g is 18 into the mass is given in kgs, so that becomes equals to 1000 multiplied by g, that is 980 dynes. Okay, so converting into dynes, Newton into dynes, we get F is equals to 18 into 1000 into 980 dynes. So again the pressure on the pressure on applied on the liquid is force upon area. So this force is 18 into 1000 into 980 upon area is 1200. So that becomes equal. So if H is equals to, if H is the amount of height that will rise in the liquid, if H is the amount of height that will rise in the liquid, then P is equals to H rho G. So the equation we have H into rho, which is equals to 1 into G, that is 980. So that becomes the rise in the pressure, that is force, which is equals to H into 1 into 980 is equals to the force applied, that is 18 into 1000 into 980 upon 1200. So the height rises 15 centimeter, comes out to be the value. So A is the correct option. A body floats in the water with 1/3 of the volume above the surface of the water. If it is placed in oil, it floats with half of its volume above the surface of the oil. The specific gravity of the oil is, okay, so the weight of the body will be equals to the weight of the water displaced or the weight of the oil displaced, that is weight of water displaced or the weight of oil displaced. Okay, so we have the total weight in the water is, it is 1/3, it is 2/3 of its volume above the surface of the water, and it is half of its volume above the surface of the water. So 2 upon 3 of its volume in water, which is equals to half of its volume in oil. For oil we have O, for water we have W. Okay, so the density of oil is equals to, in terms of the equation in terms of density becomes rho rho 0 rho O is equals to 4 by 3 rho W. Okay, so the specific gravity of the oil is equals to rho 0 upon rho W, that is equals to 4 upon 3. So B is the correct option. A jar is filled with two non-mixing liquids and two having densities rho 1 and rho 2 respectively. A solid ball made up of material of density rho 3 is dropped in the jar. It comes to equilibrium in the position shown in the figure. Which of the following is true? So if the ball is at the center, jar is filled with two non-mixing liquids, so it comes to the equilibrium after leveling both of them. So in the equilibrium position, the mass of this will be equal to the weight of the first liquid upon to the weight of the second liquid. That means the addition of both the liquids will be equal to the mass of the ball which is put in. So, okay, so we have at equilibrium position we have V rho 3 density of the third of the ball equals to the densities of the two liquids, that is V rho 1 G plus V, okay, half, they are half filled, so half of the rho density of the first liquid to the half of the density of the second liquid into G, so that becomes equals to rho 3, which is equals to rho 1 plus rho 2 upon 2. Okay, so rho 3 lies in between the rho 1 and rho 2 in the scene. The rho 1 and this is the rho 1, this is rho 2, and rho 3 lies in between both of them. So simply that the figure implies that rho of 2 is greater than rho of 1. Okay, since rho 2 is little bit density is greater than this, so we have the arrangement such as the density of the first will be less than the density of the third, and then comes the density of the second. Okay, so the density of the third will lie in between both of them. So we have C as the correct option. Rho 1 is less than rho 3 is less than rho 2. An iceberg of density 900 kg per meter cube is floating in the water of density 1000 kg per meter cube. The percentage of volume of the ice cube in outside the water is. So we need to find the percentage of the ice cube outside the water. So suppose this iceberg is floats in the water with some volume V in, which is inside the water, inside it. So in the equilibrium position, this volume inside will be equals to V in rho g will be into the density multiplied by gravity will be equals to V rho g. That is what is the volume outside. So the total volume inside will be equals to rho upon sigma upon rho into V, where sigma is the density and the total volume of the iceberg is V and rho sigma is its density. Okay, so the volume outside will be equals to the total volume minus the volume inside the water. So that will be equals to, in terms of density, we have rho minus sigma upon rho into V. Okay, so the volume outside upon volume V will be equals to rho minus sigma upon rho, that is equals to the density, which is equals to 1000 kg minus sigma, that is the density floating inside the water, that is 900 upon the density outside, that is 1000. Okay, total density is 1000, so that gives you 1 upon 10. So volume outside is equals to 10% of the total volume inside. So C is the correct option. A wooden cube floating in the water supports a mass 0.15 kg on its top. When the mass is removed, the cube raises by 3 centimeters. What is the side length of the cube? What is the side length of the cube? We need to find the length of the cube. Okay, so the decrease in the weight will be equals to the rise and will be equals to the decrease in the upthrust. Okay, so whenever the wooden cube is placed, the decrease in the weight will be the decrease in the upthrust. So that is, the decrease in the weight is its mass into mg multiplied by the upthrust will be v rho g. So cancelling the g's, we get m is equals to v rho. Okay, the mass given is 0.15, which is equals to volume. The volume is rises by 3 centimeters, that is 3 into 10 to the power minus 2 meters, into the density is 10 to the power 3. So where A is the area of the base, so we need to find the length of the cube. So here we can have A volume is equals to, so area of the base cube is A is equals to 1 upon, solving this comes to the value 1 upon 200 meter square, so that is equals to 50 meter square. So side of the cube is L, which is equals to root of A, so it is equals to root of 50, that is equals to approximately 7 centimeters. Okay, so A is the correct option, is the length 7 centimeters. A piece of pure gold of density 19.3 is suspended to the hollows inside. It weighs 24.5 grams in air and 21.2 in water. How much is the volume of the hollow portion of the gold in any? There is no hollow portion, 2 centimeter cube, 38 centimeter cube, or 0.28 centimeter cube. So there is a piece of gold with pure density. So density of the gold piece is given as rho, which is equals to 19.3. Also the mass is given, mass is 24.5 grams. Okay, so we can find the volume, that is m upon rho, so that gives you 24.5 upon 19.3. Solving this comes out to the value 1.27 of centimeter cube is the volume. Okay, so the mass of the gold piece in water is given as 21.2 grams. So the loss in the weight of the gold in water is the original weight minus the loss in the weight, so that is 24.5 minus 21.2, that is 3.3 grams is lost in water. As so the density of the water is 1 gram, so the volume of the displaced water is, so we can find the volume, that is the mass upon the density. So mass is again 3.3 upon the density of in water is 1, so we have again 3.3 centimeter cube. So now the volume of the hollow portion of the gold will be, so the hollow portion of the gold will be the total volume, the amount which is it loses in the total weight in water, that is 3.3, minus the its original volume, that is 1.27, that is the total volume in water minus the original volume. So that is equals to 2.03 centimeter cube, that is approximately equals to 2 centimeter cube of hollow portion is there in the gold. So 2 centimeter cube. A body of density rho 1 is counterposed by a weight of mg and density rho 2 in air of density rho. Then the stress mass of the body is, so we have here the actual mass of the body. So m0, suppose we have the body of density rho 1 is counterposed by a weight of mass mg and rho m2 in air and density rho. So they are given in air. So let's suppose m0 is the mass in vacuum of the same body. Okay, the apparent weight of the body in air is will be, so apparent weight of body in air will be equals to the weight of the will be equals to the apparent weight of the weight used in the air. So that is equals to the actual weight minus the upthrust due to displacement to displaced air. Okay, so we have the apparent weight is equals to in air is equals to m0 g, that is in vacuum, multiplied by the multiplied by g when it comes in contact with the accelerating gravity, minus m0 upon rho 1, that is the actual mass in vacuum, upon rho 1 into rho g. Okay, that is the density of the air, that will be equals to actual upthrust due to the displacement, that is equals to mg will be the actual weight minus the upthrust due to displacement is m rho 2 into rho g. Okay, so solving this we get m0 which is equals to m 1 minus rho upon rho 2 upon 1 minus rho upon rho 1. Okay, solving the above equation we'll get this value, so that means correct option is D. Okay, so here we have the considered that the mass m0, let we have a mass of body m0 in a vacuum. Okay, so apparent weight of the body in the air will be equals to the apparent weight of the weight used in the air. Okay, so that will be equals to the actual weight of the body minus the upthrust that will be happening due to the displacement in the air. So we have got the actual weight, apparent weight minus the actual weight, and then we have to solve the problem. A tiny sphere of mass m and density x is dropped in a tall jar of glycerin of density y. When the sphere acquires terminal velocity, the magnitude of the viscous force acting on it is. Okay, so we need to find the magnitude of the viscous force which is acting on it, on the liquid, on the ball is. So we have a tiny ball which falls with constant velocity. When the viscous so when the ball will fall with a certain velocity, the viscous force will be equals to its weight of the viscous force will be equal to the weight of the ball. Okay, so volume of the ball volume is equals to mass upon density, which they have given as x. Okay, so the mass of the liquid when the volume drops in the liquid, so mass of the liquid displaced by the ball, we can take that mass as m prime. So that becomes equals to the total mass into the density into y of the liquid. Okay, so the total displaced mass will be, so the total volume of the mass multiplied by the density of the liquid, so that is the amount of water that is displaced. Okay, so we have viscous force, we need to find the viscous force which is equals to the mass of the ball minus the mass after falling in the liquid, so that is m prime g. So that force becomes equals to m minus m prime g, so that is equals to again m minus m prime is my upon x into g. Okay, so f is equals to mg, we can have 1 minus y upon x. Okay, so C is the correct option. We have a ball of radius r and density rho falls freely under the gravity through a distance h before entering the water. The velocity of the ball does not change even after entering the water. Even on entering the water, if the viscosity of the water is eta, the value of h is given by. Okay, so the velocity of the ball v when it strikes the water surface will be v is equals to under root 2 gh. Okay, when the water will be striking the on the water surface, when the ball will be striking the water surface, the velocity will be v equals to under root 2 gh. So the terminal velocity of the ball inside the water is given by, the terminal velocity is given by 2 by 9 r square g rho minus 1 upon eta. Okay, so we know that the velocity before and after both are equal, so we will equate both of them. So under root 2 gh is equals to 2 by 9 r square g rho minus 1 eta. Okay, so getting this equation in terms of height h, we need to square this, so that becomes 2 upon 81 r raised to 4 g rho minus 1 upon eta the whole square. So this is the equation 2 upon 81 r raised to 4 g 1 rho minus 1 eta square. So C is the correct option. A wind with speed 40 meters per second blows parallel to the roof of this house. The area of the roof is 250 meters per second. Assuming that the pressure inside the house is atmospheric pressure, the force exerted by the wind on the roof and the direction of the force will be. So we need to find the force exerted by the wind on the house. Okay, so we are given with the speed of the wind, we are given with the area of the roof. Okay, so we have the pressure. Basically, firstly we need to find the pressure applied by the wind on the roof will be the amount of force they are applying per unit area, so that will be half rho v square. So the equation in terms of force becomes half rho v square into the amount of area, so that becomes half into rho is the density that is given as 1 point, wait just a second, the area of 250 centimeters, that is the pressure inside the house, 1 atmospheric pressure, so 1.2 into velocity is given to be 40, so it becomes 40 square multiplied by the area, that is 250 square centimeter square, okay, meter square, so 250 meter square. So on solving this we get the equation 2.4 into 10 to the power 5 newtons is the amount of force applied by the roof, by the amount of pressure applied by the winds on the roof, and that pressure will be in the direction, so net force acting on the roof will be in the upward direction, so this much of force is applied in the upward direction, so we have 2.4 into 10 to the power 5 in the upward direction, so we have taken the rho. A wooden ball of density rho is immersed in water of density rho to a depth of h below the surface of the water, then it released. To what height will the ball jump out of the water? Okay, so we have a wooden ball which is of density rho and it is immersed in water, applying some pressure, and then we have to find the height by which the ball will jump outside. So here let V with the volume of the ball, then the effective upward thrust on the ball, that is upward thrust, upthrust on the ball will be equals to the V rho g minus V sigma g. Okay, so upward acceleration will be equals to A, which is the change in the total levels V rho g minus V sigma g upon V sigma. So that becomes equals to sigma minus rho upon sigma into g. Okay, so velocity of the ball on reaching the surface is given by V is equals to under root 2ah, that is the ball will be coming upwards, so it will be 2ah. So if the ball rises through a height h outside the liquid, then the velocity will be equal to under root 2g h, that will be the h will be the rise in the height. So we have the two equations, under root 2ah equals to under root 2gh. So we need to find the capital H, that is the height up to which the ball will rise, so that becomes ah upon g, that is equals to, again putting the acceleration, we have rho minus sigma, sigma minus rho upon rho, gh upon g, so that becomes rho upon sigma, sigma upon rho minus 1 into h. So sigma upon rho minus 1 into h, that is D is the correct option. A disc of paper of radius r is floating on the surface of water of surface tension T. If r is equals to 20 centimeters and t is equals to 0.70 Newton per meter, then the force on the surface tension on the disc is. So we have asked to find the force on the surface tension of the disc. So we know that the force on the disc is equals to t into circumference of the disc. So that is the amount of tension, surface tension. So we have 7 into 10 to the power minus 2 is the tension. 7 into 10 to the power minus 2 into the tension into the circumference, that is 2 pi r. So that becomes equals to 7 into 10 to the power minus 2 into 2 into 22 upon 7 into the radius, that is 20 into 10 to the power minus 2. As it is in centimeters, we are converting into meters. So that is 8.8 into 10 to the power minus 2 Newton. So B is the correct option. A liquid is contained in a vertical tube in a semicircular cross section as shown in the figure. If the angle of contact is 0, then the ratio of the force of surface tension on the flat side to the curved side of the tube will be 1 upon pi, 3 upon 2 pi, 1 upon 4 pi, or 2 upon pi. So we are having the effective length of the flat part, that is equals to the liquid contains a tube in a vertical tube or a semicircular cross section. If the angle of contact is 0, then we will be finding the ratio of the surface tension on the flat side. Okay, so the effective length on the flat side, length on the flat side is equals to twice the radius, twice r. So effective length on the curved path, length on the curved path is equals to pi times r, so that is pi r. So we have force is equals to tension upon length, that is the T into L, sorry. So we have force is equals to T into L. So for the two forces we will be having a ratio. For the ratio of the force of the surface tension on the flat side, for F1 and F2 we are having T upon T, one on the curve on the flat side, that is 2r, and one on the curved side, that is pi r. So the ratio will be 2 is to pi. So the required ratio is 2 is to pi. So we have the correct option D. A rectangular film is extended from 4 into 2 to 5 into 4 centimeters. If the work done is 3 into 10 to the power minus 4, value of the surface tension of the liquid is. So we are calculating the rectangular film which has two surfaces. Hence the increase in the surface area is delta A. That is, we are having the difference between the two surfaces multiplied by the 2 multiplied by 2, as we have two surfaces, so we get the area is 24 into 10 to the power minus 2. So we will be finding the value of the surface tension on the liquid. So tension is equals to work done into upon the total area. So that is 3 into 10 to the power minus 4 of work done is on an area of 24 into 10 to the power minus 4. So the work done is 0.125 Newton per meter. That much of work is done. So C is the correct option. A mercury drop of radius 1 cm is broken into 10 raised to 6 droplets of equal size. The work done is, the tension is given as 3.5 into 10 to the power minus 2 Newton per meter. So work done is dW, which is equals to T into 4 pi into nr square minus r square. So r becomes equals to n to the power 1 by 3 r cube. So here the radius, the number of droplets is 10 raised to the power 6. So we put 10 to the power 6 as n. We get r equals to 10 to the power 2 r. Okay, so the radius given is 1 centimeter, so here we will be applying 1. Now substituting the values in the above formula, T into 4 pi into 10 to the power 6 into r upon 10 to the power 2 the whole square minus r square. Applying this formula, we get the value as joules as 4.356 into 10 to the power minus 3 joules as the power. So C is the correct option. If the value of the excess pressure in a soap bubble is 4 times than the other, then the ratio of their volumes will be. So we have one pressure, which is soap pressure, will be 4 times than the other pressure. So we need to find the ratio in the volume. So firstly we have P1, which is equals to 4 times P2. So we can have this equation P1 in terms of RA. We have 4T upon R1, which is equals to 4 times of 4T upon R2. Okay, so the ratio for R2 and R1 is R2 is equals to 4 times R1. Okay, then we have the equation for volume. V is equals to 4 by 3 pi r cube. So we have two volumes, V1 upon V2. We get the equation as R1 upon R2 cube. Okay, so V1 upon V2 is equals to R1 upon R2 the whole cube. which is equals to the ratio is 1 upon 4 the whole cube. So 1 upon 4 cube becomes 1 upon 64. So the ratio to the volume of one with respect to the other becomes 1 is to 64. So B is the correct option. The excess pressure inside a soap bubble is twice the excess pressure inside a second soap bubble. The volume of the first bubble is n times the volume of the second, where n is. We need to find the value of n. So, solution. We have the equation P, which is equals to 40 upon R. Okay, so we have here two soap bubbles. So we have two pressures P1 and we have two R1s. So P2, the equation becomes 40 upon R2. So we have the pressure inside the soap bubble is twice the pressure excess pressure inside the second soap bubble. So pressure inside one is twice the pressure inside other. Okay, so the ratio in terms of R1 is 1 upon R1 is equals to 2 times 1 upon R2. So R1 upon R2 will be equals to 1 upon 2. Now we'll find the equation in terms of volume. We know that V1 is equals to 4 upon 3 pi R cube, that is R1 cube. Again V2 will be equals to 4 upon 3 pi R2 cube. Okay, so the volume of the first is n times the volume of the second. So V1 is equals to n times V2. Okay, so we are having the changing the equation. We have 4 upon 3 pi R1 cube is equals to n times 4 upon 3 pi R2 cube. Okay, so R1 cube is equals to n R2 cube we will get from this equation. Okay, so n becomes equals to R1 upon R2 the whole cube, that is equals to R1 upon R2 is 1 upon 2. So 1 upon 2 the whole cube becomes 1 upon 8. So that is the answer for 0. Answer comes out to be 0.125, where D is the correct option. The pressure inside two soap bubbles are 1.01 and 1.02 atmosphere respectively. The ratio of their volumes is. So here the pressure is given, we need to find the ratio of their volumes. Okay, so pressure inside 1 is 1.01 and pressure inside 2 is 1.02. Okay, so in terms of atmospheric pressure we have the equation P0 plus 40 upon A, where again we can have here P0 plus 40 upon A. Okay, where P0 we are having is 1 atmospheric pressure. Okay, 1 atmospheric pressure. So the equations are 40 upon A is equals to 0.01. Okay, so and 40 upon, we can take this as B for the another one. B is equals to 0.02. Okay, that will be, here it comes 1, here it comes 1, so that becomes 1 minus 1.01 minus 1 and 1.02 minus 1. So the equations upon, so the ratio of A upon B will be equals to 2. Okay, so V1 upon V2 is equals to A cube upon B cube, which is equals to A cube upon B cube, that is equals to 2 upon 1 the whole cube, that is 8 upon 1. So the equation is, the ratio is, or to the volumes is 8 is to 1. So 8 is to 1, C is the correct option. Next, in a capillary tube, the radius r, a straight thin metal wire of radius small r, is inserted in symmetrically, and one end of the combination is dipped vertically in water such that the lower end of the combination in the same is at a same level. The rise of the water in the capillary tube is. We need to find the rise in the water of the capillary tube. So we have the equation for the rise in the height, level of the height to which the capillary rises, that is H is equals to 2t cos theta upon R rho G. Okay, this is the thing. So for the water, the cos theta will be equals to 1. So cos theta becomes equals to 1 for water. Now the T is the surface tension, rho is the density, G is the acceleration due to gravity. We need to find the equation for the height up to which the water level will rise. Also the radius of the capillary tube becomes, so here the R is the radius of the capillary tube, so that will be equals to the, it will be after the metal wire is inserted, the radius becomes r minus r. So therefore the equation for the height will be 2t upon the cos theta becomes 1 and r becomes r minus r rho g. So this is the height, that is equation number C. Option number C is the correct option. Water rises to a height of 4 centimeters in a capillary tube. If the area of cross section of the tube is reduced to 1 upon 16th of the former value, then the water will rise to a height of. Okay, so we need to find the water in the height of. So height of the water is given by the formula 2t cos theta upon r rho g. Okay, so that is the r rho g is the formula. So we have the water rises to a height of 4 centimeters. So we have, in the area of cross section of the tube is reduced to 1 upon 16th of its former value, then water will rise to a height of. Okay, so here we have to make the changes in the equation. 2t cos theta upon the r becomes smaller, rho becomes d and g. Okay, so here the height is inversely proportional to the radius. Okay, so if we have h2 upon h1, then it will be r1 upon r2. Okay, so the area of cross section, the ratio to the area of cross section of the tube is a1, that is a2 upon a1 is equals to 1 upon 16. So that is a2 is equals to 1 upon 16 a1. Okay, so in the same way we have r2 square, which is equals to 1 upon 16 r1 square, or the ratios of the radiuses are r1 upon r2 is 16, that is 1 upon 16 goes inversely, that is 16. Okay, so if the ratio of their heights to the radiuses is r1 upon r2 is 4, which is equals to their height h2 upon h1, then it is also equals to 4, then h2 will be equals to 4 multiplied by 4, that gives you 16 centimeters is the height in the rise. So that is b is equals to 16 centimeter. We have, first we take the equation for the rise in the water, rise in the capillary tube, height of the water in the capillary tube. We change the equation to r2 dj, and then we get that the height is inversely proportional to the radius. So if we have h2 upon h1, then we will be r1 upon r2. Then we have given is the area of cross section. Area is r square, so area of cross section is a2 upon a1, that is 1 upon 16. So from that area we find the radiuses, that is r2 square upon r1 square. So for r1 upon r2 we get the value to be 4, and that is inversely proportional to the height h2 upon h1, that is 1 upon 4. So the 4 and 4 gets multiplied and we get the answer 60. A capillary tube is kept vertical with the lower end in water, the height of the water raised in the capillary tube is 4 centimeters. If the length of the capillary tube is made 2 centimeters, then the angle made by the water surface in the capillary tube wall is. We need to find the angle over here. So we have the equation for the height is 2t cos theta upon r rho g. Okay, so the height in the capillary tube is 4, so 4 centimeter is equals to 2t cos, and the height of the rod in capillary tube is 4 centimeter if the length of the capillary tube is 2 centimeters. So if the theta is 0, then we have 4 r rho g. So that is, what is the angle made when the capillary tube rises to 2 centimeters? So if the length of the capillary tube is 2 centimeters, then the angle made by the water surface in the capillary tube to the wall. So we need to find 2t cos another theta 2 upon r rho g when the length of the capillary tube is 2 centimeters. Okay, so we'll take the ratios, that is cos when it was theta 2, cos 0 when it was theta 2, it was 1 upon 2. Okay, so 4 upon, we take the ratios of these two equations, theta ratios of these two equations, we get 1 upon 2 as the value. So theta 2 becomes equals to cos 0 becomes equals to 1, this becomes equals to 1, so 1 into 1 for 2 into 1, so cos theta 2 into half is equals to into 2 is equals to, wait just a second, cos theta 1 theta 2 into 2 is equals to 1, so that is equals to theta 2 is equals to 60 degree. Okay, so 60 degree is the correct option. There is a small hole in a hollow sphere. Water enters in it. When it is taken to a depth of 40 centimeters under the water, the surface tension of the water is 0.7 Newton meter per meter. The diameter of the hole is, okay. So there is a small hole in the sphere. So we can have the equation that 2 times tension upon r upon the radius is equals to h rho g. Or changing the equation, we can have uh, 4 times t upon 2r is equals to h rho g. Okay, so 4 times t upon 2r, twice the radius is the diameter d, which is equals to h rho g. Okay, so the diameter d becomes equals to 4t upon H rho g, that is 4 into the tension is given as 0.07 upon height is 40 centimeters, that is 0.40 into the density is 10 to the power 3 into 9.8, so the diameter comes out to be 1 upon 14 millimeters. Okay, so C is the correct option. The pressure at a point inside a liquid does not depends on A. Nature of the liquid, B. Shape of the container, C. The depth of the point below the surface of the liquid, or D. The acceleration due to gravity at that point. So the pressure at a point inside a liquid, it depends on acceleration due to gravity at that specific point. It also depends on the depth of the point below the surface of the liquid. The pressure goes on increasing at the lower the surface of the liquid. Next, then it also depends on what type of the liquid it is. Also it depends on the nature of the liquid. So what it doesn't depend on is the shape of the container, so it is independent of the shape of the container. So the pressure on the point inside a liquid does not depend on the shape of the container. The height of the liquid column in the capillary on the surface of the moon, if it is in 6 centimeter on the surface of the earth. Okay, so if it is 6 centimeter on the surface of the earth, what will be the height on the surface of the moon? So acceleration to gravity on the earth is 1 upon 6 times to that on the moon is 1 upon 6 times to that of earth. So therefore if the height is 2t r rho g, that is height on moon upon height on earth is equals to gravity on earth upon gravity on moon, so that becomes equals to 6 times, which is equal to 6 times. So therefore we have hm upon he equals to 6. So height on moon is equals to 6 times he, so therefore height on moon is equals to 6h. Okay, so therefore the answer is 6h. C is the correct option. Assume that a drop of liquid evaporates by decreasing in its surface energy so that its temperature remains unchanged. What should be the minimum radius of the drop for this to be possible? The surface tension T, density of the liquid rho, and L is the latent heat of vaporization. Okay, so we have to assume that the drop of liquid evaporates by decreasing its surface energy so that the temperature remains unchanged. Okay, since the temperature here it is constant, the decrease in the surface energy is equivalent to its latent heat. So therefore we have the mass change in the mass multiplied by the latent heat is equals to area multiplied by the temperature. So for the latent heat we have the equation for the mass is 4 upon 3 pi r cube rho into the latent heat is equals to T into D into the area is 4 pi r square. Okay, solving this equation we can have 4 upon 3 pi, the r gets cancelled, so we have rho L D into r cube, which is equals to T 4 pi D into r square. Okay, now that will get cancelled, so we have the equation to be 4 pi rho L r is equals to 4 pi T 2, and this is r is here the r square becomes equals to 2r and r cube becomes equals to 3r, so we are differentiating with respect to r over here, so this becomes 3r square and this becomes 2r, so we are having 3r square over here and we are having 2r square over here, so 3 and 3 gets cancelled. Okay, so rho l r is equals to t2, so the radius for this liquid drop is equals to 2t upon rho l. Okay, so 2t upon rho l is the correct option, D. R, V and rho are respectively the radius, volume and the excess of pressure for the bubble R, V and P or a drop. Then PV is directly proportional to R, PV is directly proportional to 1 upon R, PV is directly proportional to R square or inversely proportional to R square. We need to find the ratio of the pressure with respect to the ratio of pressure into volume with respect to the radius. Okay, so we know that P pressure is equals to 4T upon R. Also volume is equals to 4 by 3 pi r cube. Okay, so multiplying both of them, that P into V gives you 4T upon R multiplied by 4 by 3 pi r cube, so that becomes equals to 4 and upon 3, that is r square, so that becomes 16T pi r square. Okay, so PV is equals to is directly proportional to r square. From the above we can get PV is directly proportional to r square, so C is the correct option.